infinite series. We're going to approach this through Taylor polynomials. So do you remember the Taylor polynomial for sin x? Anybody have it memorized yet? It's an odd.
Is it? It's x minus 3 x, or x cubed over 3 factorial plus x to the 35 factorial.
Okay. Minus yada yada yada, right? Okay, that's a Taylor polynomial of degree 5, correct? Right. With that, could we approximate the sin at 1? Right, by plugging 1 in, right? Okay, so not necessarily going to continue. Okay. What we know is this is an approximation, correct? Okay, so a series, an infinite series, we will call this actually a Taylor series. And we'll get to this more at the end of this chapter, but a Taylor series is an infinite sum, okay? So we won't say a Taylor series of degree 5. We'll say a Taylor polynomial of degree 5, it stops. The Taylor series, notice the equal sign, not the approximate. You're going to go out an infinite number of terms. That means it's going to be exact, right? There's going to be no remainder and no error. So this would be x minus x cubed over 3 factorial, x to the 5th, 5 factorial. All right, and you just keep going, right? Do you want to keep going? No, you don't. But you have to note that it keeps going. Okay. That'll be a Taylor series.
How many do you have to write down before you can go to
Okay. When we work with Taylor series, we're going to have a general formula with ends in it. Okay. But for now, this serves our purposes to give you the idea of what a series is. Okay. We can approximate the sin of 1, right? Oop, that should be a 1. Same method as before. Boy, okay. Rein in that hand. Right? And that would be an exact sin of 1. Okay. What? Okay, is it converging? So, and how do we determine if it converges? That's the big thing right here. So what is it converging to? Probably the actual value of sin at 1, right? I didn't take it. And how do you determine that? Yep. Hello. Yeah, Dominic and David. Good. Thanks. Just get so excited. Oh, man. Okay. Okay. I'm
just going to clap against this and go out too.
Yeah, about twice a year, we have a whole staff meeting and they say you got to take attendance. It's got bad enough at times where they said, we're going to start counting how many times you don't take attendance, and if it gets above 3, we're going to take some action, like disciplinary action. I've never had that. But, yeah. So, okay, so are you okay with me calling this these terms, term 1, term 2, term 3, etc.
Yeah.
Right? Okay, so convergence is determined by partial sums. Okay, this is probably your most important thing of the day. For a series, do the partial sums converge? Okay, so what is the sum of term 1? 1, right? Okay, but what is the sum of the first two terms? 1 minus 1/3, right? Okay. What is S3?
Yeah, it's 1/6.
Because it's 3 factorial. I thought that didn't look right. Okay, what's S3?
1 minus 6, 1/4.
Yeah.
1/4.
Okay. Ooh, we got an extended pager here. S4 and 6 plus 1 less. Minus 7 factorial.
I don't want it.
Come on, what's 7 factorial? Anybody?
Let's see.
I'm so smart that I know it's 50/40. Because I can read. Okay. All right. So the question: what are these decimals? This. Okay. So this is.
Usually use this calculator.
Yeah, David's all over that technology. That's 8.4.
Those fractions are a lot less messy.
Okay. Does anybody have a calculator in their possession? In radians mode, type in sine 1.
Just sign 1.
Yeah. Go up many decimal places.
0.841470984.
Okay, good enough. Okay, so that's the actual value sine at 1, right? Look at these values. 1, 0.833, 0.841. Are we starting to match a little better? 0.841468. Are we getting closer to this? Okay, if we continued, we would see that these partial sums, so if I took the limit as n approaches infinity of s of n, so this means the infinite partial sums, right, converge to the actual value for sine of 1.
But I thought sine was infinite.
Okay. No, this is just a specific value of sine, and we're estimating it here, right? So the estimate gets closer and closer as we go to infinity. Does that make sense?
Yeah.
Okay. So yeah, so this is how we determine convergence for an infinite series. We look at the partial sums and what they converge to. If anything, some of them will diverge. Okay. Again, those tests that I handed to you are going to do this for you. Okay. So we don't have to do this every time, but this is the idea of what we need. Okay. Good with that?
I sure don't bothers me because it says that Charlie Brown's a hero and there's a child.
What?
Sure it says you're a good man, Charlie Brown. He's my man.
far as the base much.
An infinite series, we're just gonna ignore this.
Yeah. Like most of my comments.
Converges. Okay, so this is the formal statement. We'll dive into that notation a little bit, but you've seen it before. To the sum S if its partial sums converge to S. So we would say, just what I wrote down last time, the limit as n approaches infinity of S sub n equals S. In our specific example, that was sine of 1, right? You could also write this good? All right.
I'm confused what type of problems we're gonna have.
We're getting there.
Okay.
Yeah. Yep. Okay, let's look at a couple of, let's compare sequences and series. Maybe that'll clear it up for you. So if I have a sequence that is, let's say it's 1/3, 1/9, 1/27, okay, etc., right? What's the general term for that? Okay. Yep. What does n start at? 1, right? Okay, if we wanted to write a series, where we add these terms up, right? So a series takes a sequence and adds the terms. That's how we would write the series notation. And this would be 1/3 plus 1/9 plus 1/27. Okay. That's a convergent series. If you look, if you're curious, this is a geometric series. R is 1/3. Because R is less than 1, remember sequences? R is less than 1 at convergence. Same rule applies to series. Okay. Again, I'll go over that more tomorrow, but just that's where we're headed. Does this converge? And you make it look like a geometric series? Yes, because R is less than 1/3, or 1. Okay, so that's where we're headed with that. Does that answer your question? Okay. Here's a series that diverges, that you think would converge. So the sequence would be 1, 1/2, 1/3, and this is 1/n. Okay. And that is 1 plus. That's called the harmonic series. we know it diverges. What's unique about the harmonic series? I'll let you write that down before I say this. This sequence here, if I calculate the limit at infinity, what does this sequence converge to? 0. This series converges as well. Okay. This does not converge to 0 because you're adding terms up. It's a geometric series. R is 1/3, 1 over 1 minus 1/3, 2. This it actually converges to 3/2.
How did you get that?
We'll get that formula tomorrow. Okay. It's 1 over C minus R. C is 1, R is 1/3, so 1 over 1 minus 1/3. Okay. This series, this sequence converges to 0 as well, right? 1 over infinity. But what's odd is this series diverges. It just does not go, the terms do not go to 0 fast enough. Okay, so don't count on the sequence to determine convergence. Okay, so just kind of an odd thing. This is the way it works. All right, let's look at one more series and we'll be good for the day. It's called the telescoping series. It is we're just going to investigate this numerically. It's a technique you probably won't use very often, right? But basically we're going to plug stuff in and look at the partial sums, just like we did sine of 1, and see if we converge or diverge. Okay. To do that, if I just start plugging terms in, I get 1/2, right? And then I plug 2 in, I get 1/6. Plug 3 in, I get 1/12. Okay. Can you tell if that converges or not? Just by looking at the terms we have now. No? Yes? No, you don't know, right? I don't know. You just don't know. Because of the last slide, we don't know if it converges fast enough, if the sequence would converge fast enough to 0. Okay, so we have to actually split this into a different format of partial fractions. And if you split it into partial fractions, you get that right there. Just like we did the integrals. Don't need to go into that, but that's what we're doing there. Now we can look at it and it will actually tell us what's going on. Okay, so if we're determining what?
Did you add up the sum for both factors?
Yeah, so remember in partial fractions we'd have a over n minus plus b over n plus 1. That's what a and b come out to. Okay. Right? What's S1? 1 minus 1/2. Right. Just plug 1 in. The sum of the first two terms, 1 minus 1/2, and then plug 2 in. Plus 1/2 minus 1/3. So what do we get here as our sum? 1/2, right? What about this one? Yeah, these cancel, right? So we get 1 minus 1/3. How about S3? One-third minus 1/4. Is that right? Yep. Okay. So if the halves cancel, right? Do the thirds cancel? Negative and positive? Yeah, they do as well. So we get 1 minus 1/4. Are you noticing a pattern here?
Yeah.
Okay. Yeah. Half, third, fourth, the next one's going to be 1/5. Right? So what is S sub n? The nth partial term? 1 minus 1 over n plus 1, right? Yeah, because n is 3, and that's 4, n plus 1. Okay, so this is our partial sums. Correct. So what is the limit as n approaches infinity of S of n? One, yeah. So we have, because this goes to 0, correct? So 1. So there's your demonstration that this series converges, and it converges to 1. Okay. Again, very rare that we will actually get a number, but it happens. Don't hold those in. Blow a gasket. Remember a story about a guy that held his knees in and ruptured his esophagus? There was air leaking into it.
There's a lady whose eye popped out.
That would suck.
Did your eye pop out?
Yeah, pretty much.
You know how weird it is?
But you've ruptured all the muscles around it. Still sucks. Your eye still works, but you'd have to heal. Okay, so big idea of the day. What is a series compared to a sequence? And how do we determine convergence? See, limit of the partial sums. Okay. Again, tomorrow we'll do geometric and nth term tests. So, question? Okay. Still kind of a setup day. Tomorrow you get the meat of the 10.2. And it's not going to be due until, what's today? Thursday? Tuesday. So you got some prelims. It looks like a really big assignment. But the tests you're going to see tomorrow are very straightforward. So these problems are very short. Okay, there's a lot of them, but they're short.
I like short problems. Even in a lot of the long ones.
Okay, there you go. It's not due until Tuesday.
That's so easy.
So you can start, if you want to start spiraling, there might be a few of the problems you can do for the prelims and stuff. But most of this is going to be from tomorrow. Did you just say that's reasonable?